Hello and welcome back to Calculus 2, section 9.3, Taylor series. We already defined Taylor series in 9.1, so now we're just going to see a few more examples and talk about Maclaurin series as well. So first, Taylor series. Is going to be this approximation for functions where we write it as the summation of the nth derivative computed at a divided by n factorial x minus a to the n starts at 0, goes to infinity. So this is Taylor series. We did this on the first year's day.
What's going on with that F-A-N?
This is the derivative, nth derivative. So first derivative, second, computed at a.
Okay.
It's nn.
It's NN?
No, na. There we go.
X minus A to the N.
Better?
Stop giving me free stuff. It's just going to encourage this type of behavior, Nina. This is your fault. Thank you.
Maclaurin series, as who mentioned this last class? Anyone, right? Maclaurin series is the Taylor series centered at 0, so it's just a special case. So this is just x to the n. There's no minus a. That a is actually 0. So all of the derivatives are computed at 0. And then x minus a is 0, so it's just x to the n. So this is a Maclaurin series. But obviously Taylor is the one that it's the general case, right? So for anything. It's important for us to understand that you have to center your series properly. If you are approximating function e to the x, you will write 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus x to the 5 over 120 plus ... Goes on forever. But you have to understand that this power series is useless if you are going to compute e to the 7. Because e to the 7 and these terms here diverge at that point. They're not close. So you have to figure out the power series expansion around the point where you want to compute. So e to the x is going to compute values that you want, but let's say from -1 to 1 or something like that, something close. So don't be too far away. Otherwise, you are going to introduce a lot of error. And that is going to create problems, obviously. Now, we'll see how that's used when you start to integrate. So, Taylor series, again, you have the sine of x, which we said it was x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. I did this one in class. Minus x to the 7 over 7 factorial plus ... And that condenses, you can condense this into a power series. You have -1 to the n. You can start your n at 1. No, start n at 0, right? No, start at 1, it's fine. No, at 0. Start n at 0, go to infinity, you will be dividing this by 2n plus 1 factorial. This is how you're getting your odd numbers. And you have your x to the 2n plus 1 as well. So you have all of your odd exponents, 1, 3, 5, 7, 9, because the 2n plus 1 gives you only odd numbers as you plug in 0, 1, 2, 3, 4, and so on. For 0, this is 1. For 1, 2 times 1 is 2, plus 1 is 3. And then 4 plus 1 is 5, 6 plus 1 is 7, and so on. So as you are plugging in these values, 2n plus 1 gives you the odd numbers. And you see there is the sequence for that. Now you have also cosine x, which was 1 minus x squared over 2 plus x to the 4 over, well, that's the 2 factorial, 4 factorial, minus x to the 6 over 6 factorial, and so on, which also condenses with n goes from 0 to infinity. You still have this alternating term. Start at 0. You have x to the 2n, right? 2n generates even numbers. Why? Negative 1 to the 0 is 1, right? So there are many of these. So I want you to work on one of these functions. So find the Taylor expansion around 0 for 1 over 1 minus x. Find the Taylor expansion for this, which means, and I want 4 terms. Let's start with 4 terms. So find 4 terms. Center it at 0, so it's technically a Maclaurin series. So the nth derivatives computed at 0 divided by n factorial with the x to the n, right? That's what we have. Start from 0 to infinity. Let's see what you get. So get first few terms.
No.
One of the students is parents. Really? Yeah, they're all sitting in the class. It's so good. So watch them sometimes keep their like get lost in time. Stuff I love. And I actually think it's just time about oh, you know the second verse too. There's a middle part. No, I know it's a whole song. Look, I know it's a whole song, but I hardly know the regular except theme song. Not even phase.
I was in theater and
Oh my god, I don't even know this.
So I hope you found like 5,000 derivatives here and start plugging things in. Hang on, solve itself.
It's not. God, I wish it did theater. Yeah. I've fought and lost so many of these things, but they all come with like extra buds. And it's just so much easier to tell which is left and which is right. But actually, the other little left ones are really not on there.
Yeah, that little.
Yeah, I didn't realize that, but I'm like, you know what? At least it looks cool.
Or the iPhone one has the thing on
Oh,
the
yeah, yeah.
Yeah, I'm gonna do that. What that little phone thing was?
Well, it didn't matter anyways, because at least it looks pretty cool. I have like a whole thing of extra, but I don't even use half of them because it's the middle size, it's the little, it's the small size, and it's the big size.
I just did the
I only use the little one. You did theater, huh? Most of my friends in high school were theater kids.
How far did you get with the problem? That's what I'm interested in.
Still doing the really bad problem.
Exactly. Still doing the derivatives. So I need this form to do calculations, but I need this form to continue taking derivatives efficiently. So I keep them all. So
Where is it second negative one?
chain rule.
Right. We cancel all. X minus 1.
No coughing. I'm gonna stop because I'm bored. So the expansion that we get, since we are expanding around 0, right, a equals 0, Maclaurin series, we are going to start with, well, we're going to say 1 over 1 minus x is approximated by, because we are cutting it off, there will be no plus and then dots. We have f of a, which is at 0, so that's 1 over 1 minus 0, plus the first derivative, which is 1 over 1 minus 0 squared divided by 1 factorial times x, plus next one is 2 over 1 minus 0 cubed divided by 2 factorial, which is 2 times x squared, and one more term plus, oh, I took that derivative for nothing, I guess. Last one is 5. I'm not sure what you're talking about. Thank you. Where was I? Oh yeah. CO22. 1 minus 0 to the 4 divided by 3 factorial, which is 6. I'm not even going to use the next one. So this is equal to 1 plus, this is all 1, plus, this is all 1, plus, I forgot to put x cubed there. This approximation is good for terms that are around 0. Shall we test this? Let's test this. Compute 0.3 in both, on the left and on the right. So what do you get? On the left is 1 over 1 minus 0.3, which is 1 divided by 0.7, which is what? Luckily, you're using your calculators to compute this. So this is about 1.4286. How about that? 4 decimal precision. Now compute the other side. Would be 0.3, no, would be 1 plus 0.3 plus 0.3 squared plus 0.3 cubed, which is 1.3 when you add the first ones, plus 0.09 plus 0.027. So if you add all of these, it's going to be equal to 1.31. No, that will be a 4 there. 7, right? That's it. So it's close, right? If you take a look at the two numbers, it's close. It's like 1 cent away. Now, just to see how bad this is, compute at x equals to 10. That's far away from 0 where we centered the whole thing. So if you compute at 10, on the left hand side you get 1 over 1 minus 10, which is 1 over negative 9, right? Which is negative 1.111 forever. Yeah, that's what I said. Please pay attention. Thank you. And if you compute the other one will be 10. No, it will be 1 plus 10 plus 100 plus 1,000, yes. So that's 1,100, right? So this is just really close, right? So you see what happens if you're not computing close to. You have to center this. So if you have to compute value 10.1, you will center your series at 10. So you will not be doing Maclaurin series. You will be doing Taylor series, where that a is not 0, but a is 10. You will recompute the whole thing, and then the polynomial you get when you put in 10.1, it will work out to give you the close numbers. You can spend a few hours, playing with these things at home. You'll see how it works. So, not even close. because the original problem is centered at 0, and yep, that's such is life. So you can center these anywhere. I'm going to skip over binomial series. I want to talk about the remainder. There it is. So I'm skipping over binomial series, but I will talk about the remainder. All right, so I'm going to write expansion for e to the x again. Expansion for e to the x was 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. And since I am using dot dot dot, I can use all the equal signs. So I go from 0 to infinity x to the n over n factorial. So this is e to the x expansion, and then if you do all the derivatives and stuff and you compute it, you will get that. But you see this one is centered at 0, right? So e to the x is equal to summation 0 to infinity x to the n over n factorial if centered at 0. Or e to the x is 0 to infinity all right, so x minus a to the n over n factorial if centered at x equals to some number a. Now, you have to, if you are computing e to the 3.1, you will center your expansion at x equals to 3, and then whatever polynomial you get, you will compute that at 3.1. But how many terms do you get to use? I told you, usually 4, 5 if you have time, right? And we saw that every problem we did so far, we were about 1 cent off, right? 100 or 1,000 off. So these guys converge very quickly, and we can use even less terms if we want to. But we know it's not exact. So if I am going to write e to the x and use only 4 terms, I have to put the squiggly equal sign and write 1 plus x squared over 2 plus x cubed over 6. And there's no more plus dot dot dot, which means it stopped and I truncated this power series. So it's no longer exact, so I have the squiggly equal sign, which means it's approximation. So I introduce the error now. And the error would be approximated by the first term you throw away. So most of the calculation happens in the first term, then the second term makes it better, and then the third term makes it better still, and then the fourth term and the fifth term. And in between these two, each two terms, there is this massive gap of like a step in making the calculation better. So most of the error that you are encountering will be at the first term you threw away. So in this case, error can be approximated by x to the fourth over 24. That would be the order of the error, because that was the first term. Thinking about how much the next term is going to contribute in comparison to this term, guys, next term is divided by 120. The following term is divided by 720, right? So dividing by 24 already cuts into, right? So let's say that you were computing 0.1. Let's say you were computing e to the 0.1. And you compute e to the 0.1. What is the error? It will be 0.1 to the fourth divided by 24. That is really tiny number. Zero point 1, 2, 3, 4, 5, and then 41, and then 6. Look at that. This means that the first 5 decimals are already correct, right? On the 5th term. So if you compute 0.1 to the 4th over 24, you will get 0.1, 2, 3, 4, 5, 4, 1, 6, 6, I believe 7 was the next one. Whatever you're doing, just quit. 7. I'll just copy this on the side. And now I want to go with 1 point to the 5 divided by 120. The next term would be you get the idea. Corrections to the calculation that the first 4 terms did from the 5th term would be, as you can see, 4 on the 6th decimal, and over there 8 on the 8th decimal. You don't need this precision, okay? You don't need this to create cars and bridges and things. Particle physicists would look at this stuff, and fusion people, right? That, yeah, sure, there are some applications when you are going for this stuff. But you don't need it to build a car or the airplane or space shuttle or any of those things. You don't need this. So this type of a precision. But imagine how much easier it is to work with this polynomial in terms of integrating and differentiating and doing everything else than to work with, you know, some crazy kind of e to the something and whatever else. Well, e is very easy to differentiate and integrate, but still. So what is happening with the error now? I'm going to say that the remainder on the power series, I'm going to put this red because this is my remainder, is going to be that f of n plus 1, that's the next term, divided by n plus 1 factorial x minus a to the n plus 1. And I'm just going to say n plus 1 means next term. I'll just say equal the first term we throw away. So that will be the first term we throw away. I did calculations over here for this function, 1 over 1 minus x. And you see that if we use the first 4 terms, right, we get this precision. So now I can actually compute using the term that I didn't use before, but I found the derivative for it, this one, I can compute the order of the error that I'm making by dropping the infinity of terms. So the error over here would be 24 divided by 1 minus 0.3, right? To the 5th power. Is that correct? So we are talking about 24 divided by, open parenthesis, 0.7 raised to the 5th power something is off over here because my error is now 142. What's wrong?
So you're saying if just by calculating that one next term, it gives you the error of an infinite number.
Because most is concentrated in that one term. You can see over here, I have to figure out what's wrong with this problem over here. Why is it giving 142? But you're asking the question, and here is my answer.
Oh,
right?
okay.
You see that if I cut, the one that I throw away is x to the 4 over 24, and then the next one I throw away is x to the 5 over 120. Now look how much they contribute to actually number in a sum. But you can see how much more bigger this number is than the next one. So most of the error, right, if you think about this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this one is still 1,000 times, right, 1,000 times smaller. So if you are calculating error, you just want to compute the next term, and most of the error will be in that next term. In this particular example, the next one was 1,000 times smaller. I'll have to look at that problem and see what was wrong there. Other than that, there's nothing else. We're done.
Don't you still have to divide it by the factorial? Because that's just the derivative.
Oh yeah, that was just a derivative, and then you have to divide it by the factorial. And what was the factorial?
It was
5?
506? Yeah, it was 5.
5, so divided by 120. And the error was 1.2.
I think you left off the 5, right? So you gotta do it by 7.
Oh,
No,
okay.
you left f at 4 and then made you the 5 in the equation, so 5 is the 1 3.
Yeah. This is just a derivative. So when I calculate the derivative, and then I still have to divide it by, yeah. So it is 1.19. That's better. Okay, good. Well, thank you. So that's the error. Just look at the next term. They give you the tables of these power series if you want to memorize these things. If you have nothing else to do, there they are. We compute this one earlier. These are e to the x, which we just used. Here are sines and cosines, which we also used. So these are the most frequent ones. Now, which ones you will need so you can visually pick up the patterns once you get to differential equations. you will need e to the x, sine and cosine, and then hyperbolic ones as well. Now look at the hyperbolic ones. They're the same as sine and cosine, except they don't alternate. They have plus, 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 and these guys have plus, minus, plus, minus, plus, minus. Don't you see they're the same? So this power series for them look the same as sine and cosine without the alternating minus 1 to the k term. That's it. So it's not that bad in terms of memorizing these. I memorized them because as a student, once I realized, I wasn't told this, I realized it on my own, so, it's like twice as more dear that, oh, that's all odd exponents, and that's all odd, that's how you write odd numbers. So for me it was easy to remember it, but then that realization that, wow, that's why sine is an odd function, because it's all odd exponents in there. And then cosine is even. If you look at the even ones, that's a square and a fourth and a sixth and so on. You have 2k. That creates even numbers. So that was for me like revelation. So you can memorize these guys if you want to. I don't know. I find it very easy to memorize them because of the, look. That's the difference, and look at the difference.
Oh.
It's just like nothing. And then this one, I just know because I use it a lot. These two and these two are the same. So what's the only thing that you have to kind of work on, these three? If you want to memorize them all. But anyway, at least know some of them. Good. That takes care of this section. We are going to take another 5 minutes break and then talk about the integration and derivatives and be done with this.